Hello, I am Hunter G. Cook, and this is my ECE 524 final radio system design project. So to start out with, I did a branch line coupler, and this began with just a simple signal divider that split power evenly between two ports with a 90 degrees phase shift. And then from there, I moved to non-ideal lines, so made of foil tape. Let's see if I can. Yeah. So, and if you'll notice, I have a 5mm width on the top and bottom, and about 3mm width on the left and right, and those equate to about 50 and 35 ohms. And using the TX line tool with the appropriate materials, wavelengths, resistance needed, I was able to calculate the links as can be seen. And then I had to corner those off with these T-junctions, and those just put the links together basically. So I have port 2 and port 3, both 50 ohms. And port 1, our input, would split to those. And here is the physical copy. If you'll notice on the bottom left, I didn't put a port there. I just used a 50 ohm resistor. That could have been, more close to ground, but it's as good as I got. Okay, so here's the simulated properties. On the top, you'll notice about a 92 degrees phase difference between the right side ports. And the power between them is about minus 3.7 dB. I was going for minus 3, which would be half power. And then here's the actual one. Both powers are a little bit different, not exactly minus 3 dB, but pretty close. And for the phase difference, it's quite accurate. Okay, so after that, I moved to the Wilkinson Combiner. In here, I just started with a ideal power combiner that is similar to the previous thing in that it splits the power, combines the power, but now we're getting no phase difference between the ports. So again, I use the TX line tool to work out all of these resistances for the appropriate wavelengths and materials. And then we have a resistor in the middle, 100 ohms. And then we have these taper bits to go so we can impedance match to our 50 ohm outputs, because we were coming from we were going from 70 ohms, so I wanted to go from 70 ohms to 50 ohms. And then here is the physical one. If you'll notice, these guys are quite long. Worked out in simulation, no problem. I'll show that in a moment. We had to do some extensive soldering to get everything connected. So here is our actual. And if you'll notice, you can't really tell, but on the top one, the two are overlapped, so the phase on them is exactly the same. On the bottom, there is about minus 3 dB power on both, which is really good. And then here, you'll notice that there's about minus 4 dB, but it is on both. So there is some power loss, but it's split evenly, and then the phase is near perfect, evenly matched. Okay, so for the mixer, we started out with the branch line, as you can see in there on the left side. And for the in, we just replaced it with a, and then on the bottom left, instead of having that resistor or 50 ohm port, we've replaced it with this RF input. The top becomes our LO, local oscillator. And then at the end, we connected two diodes for balancing, and then from the middle of those, it's M-limbed out to a pi filter, and then ultimately to our port. And here's what the actual one looked like. I do not have the SMD components on this far right side, but you can pretty much imagine the diodes would go between the down parts, and here the diodes there, the capacitors, and then the inductor. I did not physically put this guy together because it would have been very challenging for me to test and do some of the intricacies. So in here, I have the conversion loss. So there's about a minus 8.4 dB conversion loss between the RF and the output, which is pretty good. Here, and notice the conversion loss here. So I have my 0.95, which is minus 73 dB, and then M2, which is our output, at minus 13 dB. There is obviously not minus 7 dB there. We had the pi filter, which was doing a lot of filtering there, so we get even less at those larger harmonics. And yeah, the minus 13 is even lower as well. Okay, so for the power amplifier, here's just the very basic schematic of it. We started out by trying to figure out the optimal impedance for the amplifier core, and that ended up being 73.4 plus an imaginary 96. And so the big challenge with this was impedance matching, which is these two blocks. Here is what I believe is the output. And you'll notice we basically just played with these lengths until we found how to get the complex conjugate, which would impedance match for us. And basically just did that by opening the Smith chart, playing with those links, and getting that right. The same thing was done for the input. Basically just playing with the Smith chart until we got the appropriate values. Here's the actual constructed thing, and I will notice that the two stub lengths, I noticed in ADOBR when adjusting those, like just tiny little changes on that would really spin it around the Smith chart heavily. So I was, I initially put this thing together, and I'll show you here. This is what was simulated at 17 dB of gain, which is right at the peak of this guy. And this is what we ended up having, which looks a little odd, but I'll try to explain what happened. So when I first put this thing together, we had this this peak right here was too high, and I thought, okay, well, that stub length is probably being pretty tricky because, with the foil, there's a lot of different things. So I basically just extended that length and noticed which way it was moving and just slowly trimmed that back until I had the peak right at 950 megahertz. Okay, and then the Yagiuda Antenna, which the entire specification of this came from the Yagiuda Antenna chart. Using our 950 megahertz, we determined a wavelength of 31.57 centimeters, and it basically just outlined everything we needed. We did 3 deflectors, 1 reflector, and it had the ratios for how long those needed to be, and you can see them there, and the spacing between them at 6.32 centimeters. Yeah. And similar to the amplifier, I noticed that the 50 ohm was not perfectly at 950, maybe it was slightly above or below. I'm not 100% sure. So we basically had to do the same thing with the dipole. I trimmed the dipole just ever so slightly just to get it right at 950. The closest I could get was 44.6. It gets really touchy in there, so getting that length perfect was pretty difficult. Oh, here we go. Yeah, so marker 1, the impedance, yeah, there it is. The impedance is 44.6. I try to get that 250, the real part. Okay, and I think that is everything. Thank you.